Yeah. Hey everyone. So in this video, I'll discuss an interesting signal processing problem in which when we are upsampling a sinusoidal signal, its envelope is non-flat. Okay, we all know that the envelope of a sinusoidal signal is a flat signal, but I also found out that the upsampled version of it is non-flat. So this is a very basic signal processing problem. So yeah, let's start this then. Okay, so for this specific example, I've chosen a sinusoidal signal of frequency 70 megahertz and sampling frequency of 160 megahertz. Why 70 megahertz? I'll tell it later. Specifically, why I have chosen this. And yeah, this satisfies Nyquist criteria, where the sampling frequency is more than twice of the signal frequency. Okay, and this is how the signal looks, that it is exponential of j2 pi f naught by fs times n. So we know that envelope of this, which is kind of a absolute value of this, is a flat signal. This is how it will look. The above let's look at the below plot first, that it is the absolute value of the or the envelope of the sinusoid. This is the original signal. This is not the upsampled. It is almost flat. And yeah, the above plot is the real value of it. You may be wondering that it is not looking like cosine or sine, because yeah, the values that we have chosen, signal frequency of 70 megahertz and sampling frequency of 160 megahertz. So for this specific case, there are not enough number of samples in one period. So this is why it looks like a zigzag pattern. But yeah, I mean, for our for explaining this won't matter that much. But yeah, I'll show you one case where we have chosen 70 mega instead of 70 megahertz. If we choose a different value of the frequency. Okay, so yes, for this experiment I have used MATLAB, and for upsampling I have used interp function of the MATLAB. Okay, this is for upsampling the signal. Okay, so yeah, we will interp or upsampling by a factor of 4, and this is how the MATLAB command will look like. That this is my original signal, this is the upsampling factor, and this is the output signal, and yeah, this B is the filter coefficients. Okay, yeah, so this is the actual problem. That this is the above plot. The first plot is the real value of the output signal or real value of the upsampled signal, and the problem lies here. If we look at the envelope or the absolute value of the upsampled signal, you can see that it is not constant. It is moving a lot. Okay, so this is the actual problem. So you can pause the video here, and if you want to think about it, work out the math behind it, you can take your time. Okay, so till now this is the problem definition. I hope the problem definition is clear. Okay, we took a sinusoid, we upsampled it, and if we plot the envelope of the absolute value of it, it is non-flat. What is the reason behind it? So let's try to find out. So first, let's understand that what is upsampling or how we do upsampling. So step 1, there are basically only 2 steps. First, we introduce m-1 or we pad m-1 zeros between 2 adjacent samples, and then we pass it through a low pass filter. Okay, we pass it through a low pass filter which also interpolates the samples having 0 values. Okay, so we know that upsampling introduces imaging. So to mitigate these effects, we have to use a low pass filter, and that's how the low pass filter is also known as the anti-imaging filter. And the cutoff frequency of the low pass filter depends on my signal frequency, also depends on the upsampling factor. Okay, so to just give some basic idea, so let's say that this is my actual signal, something like this. Okay, let's assume for just simplicity that m is equals to 2. So I have to pad 1 zeros between 2 adjacent samples. Okay, so this will be my original signal, and I have introduced 110 between 2 adjacent samples. samples. Okay, and if we look at the frequency response of this, so if we know that sinusoidal is complex exponential is one impulse, after padding let's say 110 or after upsampling by a factor of 2, this impulse will repeat. This is f naught, this is fs plus f naught, this is f naught minus f naught, fs, f naught plus fs, f naught minus fs. So basically, yeah, this will repeat with a period of fs. Now we have to put a filter around this, so to only pass the fundamental. Okay, if I zoom it here, to only pass the fundamental, ideally the harmonics should not mix with the fundamental. So this is the role of the low pass filter. Or yeah, as part of this, it will also interpolate these values, the zero values, so as to it will have a least square or the minimum error with the ideal values. Okay, so that will depend on the different algorithms. Like if I use enter function, there are several other functions like resam function, which I'll also touch upon a little. Okay, so to understand this problem, we have to focus on the how we are doing the filtering. To understand this problem, let's look at the filter characteristics. So this is how the time domain plot of this specific filter looks like. But yeah, to understand this, we have to analyze the magnitude response of this filter. Okay, so this is how the magnitude response of the filter looks like. So where our signal lies, my signal is at 70 megahertz here, and we know that it introduces images. So where is the next image will fall? It will be at fs plus f naught. Fs is 160, f naught is 70, so it will be at 230 megahertz. So it will be here. So I think now you are getting that where the problem lies. This filter is only attenuating the image by only 20 dB. Because of that, because the attenuation is not much, because of that, the harmonic will mix up with the fundamental, and that is causing the signal to be not like the actual signal. Okay, so this is the reason. This is the reason that this is the reason which is causing the envelope to be non-flat, because my signal will not like the sine theta or the upsampled version of the sine theta, not the ideal case. Okay, so yeah, I mean, to explain it a bit further, so this is my actual signal, original signal at 70 megahertz. These are the various images, and ideally it should only pass this. But in our case, in this case, when we are using the interp function, it is also allowing this particular image to pass through. Yeah, obviously if we look at on a wider spectrum, other images will also pass through based on how much attenuation we are allowing the other images to be. Okay, so what we can do? So for this specific experiment, I have used another function in MATLAB, which is resamp. This is another function. This is like, yeah, I mean, we can give a fractional resampling also from this function. So this resamp function designs or uses a different or a better filter, better in terms of that it is a sharper filter. Okay, so here I'm comparing the time domain response of two different filters. Blue is interp and red is resamp function. So to compare, first thing that the filter length of interp function was somewhere around 17, and filter length of the resamp function is somewhere around 65, if I remember correctly. And yeah, just to compare these time domain plots, I had introduced zeros on the left and the right of this, just to compare them on the time domain. But yeah, the actual understanding lies on the magnitude response. If we compare the magnitude response, so blue is interp function magnitude response, red is the resamp function magnitude response. So I hope now you can relate the logics, that my signal is here somewhere at 70 megahertz, and yeah, if I look at the 230 megahertz, we can see that the other filter, the resamp functions filter, is attenuating the image a lot. It is attenuating by more than 60 dB. So which is causing the harmonic not to mix up with the fundamental, and that's how, if we look at now the envelope, this is the envelope of the upsampled sinusoid, and yeah, the red one is the interp and blue one is the resampled function. So we can see that this is much tighter now. When we use this filter, the red one, when we use the resamp functions filter, the envelope is tighter. Okay, so basically the problem lies that how we are filtering the signal as part of the upsampling. Okay, so this is the reason of this problem, or this is the why the problem is occurring. So this is one of the way that if you want to put a solution of this problem, so design a better filter. So my harmonics do not mix up, or the images, to be precise, to say precise, that my images should not mix up with the fundamental. Okay, we should not allow the images to pass through the low pass filter. Okay, so in the beginning we said that I have specifically chosen to be at 70 megahertz. The signal frequency I have chosen as 70 megahertz. What if I choose a lower value? So in this case I have used 20 megahertz of signal. Same sampling frequency is 160 megahertz, and yeah, in this case the performance of both the filters, interp and resample, are almost same. Okay. Yeah. Okay, so I think the problem and the solutions are almost clear now. And yeah, ignore the initial and last transient. This is the number of samples that filter is taken to settle up. Just focus on the middle part. In this case, the performance of both the filters are almost same, because if we come here, when the signal frequency is 20 megahertz, the image will be at 160 plus 20, 180. Here, I should use a different color. Yeah, the 20 megahertz image will be here. So in this case, both the filters are attenuating the image by more than or equal to 60 dB. Okay, so I think the problem and the reason and how we can make it better is almost clear now. So this is because of the filter response of the upsampling, because upsampling is two-part process, pad zeros, then pass it through a low pass filter. Okay.